Okay, so we finally actually get to start on some real number theory, and we need to start talking about rings of integers. So, um, probably like one of the broadest goals of algebraic number theory is to understand these so-called rings of integers. So the main goal of algebraic number theory, or one of them, maybe it's not totally kosher to say the main goal, algebraic number theory is to understand the structure of rings of integers and finite extensions of Q. So you might, I guess, so one natural question at this point is, what is a ring of integers? Well, I'm about to define it, but it's really just a generalization of the standard integers inside field extensions of Q. And kind of the hope, I guess, in some ways, is that studying these generalized rings of integers actually helps us learn a little bit more about z, so our familiar integers. So first, let me tell you what these rings of integers are. Okay, so definition. I'm going to let A be an integral domain. And I'm just going to let L be any field containing A. An element alpha is said to be integral over A. If there exists a monic polynomial, so this monic is kind of key in this setting. If there exists a monic, so remember this means that the weighting coefficient is 1. A monic polynomial f in a adjoint x with alpha as a root. Okay. So, for example, you could consider the following. I'm going to let this is kind of like maybe one of the motivating examples. I'm going to let A be Z, let A be Z, and I'm going to let L, let's say this is Q adjoin I or something like this. Okay. It turns out we'll see something like I is integral. I is integral over Z, or just integral. Okay. When we're talking about Z, a lot of times we'll just say it's an integral element of L, or it's an element of the ring of integers. We'll see. I is integral over Z. it's a root of x squared plus 1, but something like maybe I over 2 is not. Integral over z. So you have to do some work to check that something isn't integral over z. It turns out, so an element is integral if there exists any monic polynomial with coefficients in A that has alpha as a root. It turns out, and we'll prove this later, that alpha in L is integral over A if and only if the minimal polynomial if and only if the minimal polynomial of alpha over, let's say, the field of fractions of A has coefficients in A. So it's enough to compute the minimal polynomial. In this case, the minimal polynomial of I over 2 is x squared minus or plus a quarter, and this definitely does not have coefficients in Z. The primary goal of the next couple sections is to give two different proofs of the following theorem. So, theorem, I'm going to let L be a field containing an integral domain A. Then the elements of L, which are integral over A, these form a ring. And this ring is called the ring of integers of L. Okay. So, I'm going to say here. So, we're going to call this collection the ring of integers, and we won't know it's a ring until the end of this lecture. There are two primary ways, at least two ways that Milton proves this result. The first is using the theory of symmetric polynomials, which is kind of like more elementary, and the second is using some more general module theory stuff, which ends up being slightly more general, but as a byproduct is slightly more useful in many settings. Okay. So the issue here is essentially if I have alpha, which is the root of some polynomial f, and beta, which is the root of some polynomial g, how do I know that there's some polynomial which has a root alpha plus beta or alpha times beta? It's not as simple as just taking the sum of the polynomials or the product of the polynomials. So there's some work to be done. Okay, so first we're going to prove this using symmetric polynomials, and that's what this lecture is going to focus on. So first I should tell you what a symmetric polynomial is. So definition: a polynomial in multiple variables p say x1 through xr, and A here is still an integral domain. I guess it doesn't really matter for this definition, but if you're wondering what A is, you can just take it to be an integral domain. It's said to be symmetric if it remains unchanged after swapping the variables. So okay, so something like, so for example, I guess formally, what do I mean by this? Formally, this means P of x sigma 1 x sigma r, these are the same polynomials for any permutation sigma in the symmetric group on R letters. Okay, they're kind of an important family of symmetric polynomials. These are called the elementary symmetric polynomials. So the following are the elementary symmetric polynomials in R letter, or I guess I would say in R variables. Okay, there are going to be R of them. S sub 1 is going to be just the sum of all my variables. S sub 2 is going to be the sum over I less than j, x sub I, x sub j. S3 is going to be the sum. So I guess maybe I'll just tell you what in general they look like. S sub n is going to be the sum over subsets I of the indices 1 through r, I of size n, of this guy x sub I, where x sub I, if I is a set of indices, just means take the product of x sub little I for every I and big I. So where x sub indexing set is the product over little I and I, x sub little I. And the following theorem essentially says that in some ways the elementary symmetric polynomials are the only ones you really need to care about. So I should really, sorry, there's missing an in general. So the theorem, this is called the symmetric function theorem. And it says, I'm going to let A be a ring. Then every symmetric polynomial P on our in our variables is a polynomial in the elementary symmetric functions with coefficients in A. So essentially what this is saying is that, well, one way to say this is symmetric polynomials form an algebra, and these guys, S1 through SR, generate that algebra over A. Okay. So let's go ahead and prove this. The proof is kind of similar to something you might see when you're learning about Grosvenor bases and algebraic geometry. You won't need to know anything about them, but if you've seen them, then this should look probably mildly familiar. So first, we're going to give this thing a monomial order. There are lots of monomial orders. So what do I mean when I say a monomial order? It's just a way of comparing two monomials and saying which one is bigger. Bigger being in quotes. So first, give this thing a monomial order. So how do we compare two monomials? Well, we say one monomial, x1 I1 through xr IR, is bigger than another if one of the following two things happens. Okay. Either the total degree of the left is bigger than the total degree of the right. So if either the sum of all these i's is bigger than the sum of all the j's, or we have equality all the way down the line, or equality holds, or equality above holds. And for some s, I1 equals J1, IS equals JS, but I sub s plus 1 equals J sub s plus 1. So essentially this says, first compare the total degrees. If the total degrees are the same, then just go down the line, and the first time you hit one that's different, the bigger one determines the bigger monomial. Okay. So intuitively, this order considers total degree first, and then weights. The degree of xi more than xj. If I is greater than j. Okay, so this essentially is a total order on the collection of monomials with coefficients in, or I guess not even, it's just a total order on the collection of monomials in R variables. Okay. So I'm going to let P be a symmetric polynomial. And I'm going to let x1 to the k1 times xr to the kr, I guess, symmetric polynomial in ax1 through axr. And I'm going to let this thing be the biggest, the maximal monomial in P with respect to the above order. There are some like remarks I should make, which are that if two monomials are not equal, then one is necessarily greater than the other. So essentially, if two are not equal, then I can find either their degrees are different, or if their degrees are the same, I can find some power that doesn't match, and then that will determine which one is larger. So I'm going to let this be a maximal monomial in P with respect to the above order. Okay, with non-zero leading coefficient C, I guess with non-zero C and A. Okay, so since P is symmetric, it has to basically contain every other monomial that's a permutation of this monomial. Since P is symmetric, we can basically assume, I guess not only can we assume, we're guaranteed that K1 is greater than or equal to K2, which is greater than or equal to. So what's the logic here? So let's think about this for a second. If I have this monomial, I can apply a permutation which puts K1 greater than K2. It orders the k sub i's based on their size. Applying that permutation, I see that P actually must have that same monomial because P is symmetric. So that, based on the way this order works, it would pick that one as the maximal one. Okay. So we have to be guaranteed that these k sub i's are monotonic, non-increasing. Okay. So thinking about S sub I, the ith symmetric polynomial, or the ith elementary symmetric polynomial, we see the maximal monomial in S sub I is x1 through xi. Okay. So consider s1 to the d1, sr to the dr. The maximal monomial in this guy maximal monomial here is going to be x1 to the d1 plus d2 plus dot dr, x2 to the d2 plus dr, and so on. Okay, product times xr to the dr. Okay, so this is kind of one of those things where you really just need to sit down and work out a couple examples to see how this works. Essentially what's going on here is that in S sub I, I've got a factor of So the maximal monomial is going to be the product of all the maximal monomials in each s sub I to the dth power, the d sub ith power. And I'll have d1 x1s in S1, I'll have D2 X1s in S2, so on and so forth, on down the line. Okay, so the goal is essentially to cancel the leading term in P with a leading term in one of these guys. And we can essentially do this. We see P of x1 through xr minus c times, so if I take d1 to be k1 minus k2, d2 to be k2 minus k3, and dr to be kr, then the leading monomial here is going to be strictly smaller than, let's see, strictly smaller. Leading monomial. Than P. Okay, I've basically canceled the leading monomial in P by subtracting off this polynomial in the s sub i's. It should be an S1. Okay, and essentially you can repeat this argument, and after a finite number of steps, you'll see that P is a polynomial. So we can repeat this argument with, maybe I'll call it P prime equals P minus C S1 to the K1 minus K2, S2 to the K2 minus K3, and so on. SR to the KR. Okay. Okay, and after a finite number of steps, we'll have written P will be a polynomial in the s sub i's. With coefficients in A. There's another way maybe that makes more sense to make this argument run, is you would take not just any P, but maybe the symmetric polynomial whose, this is maybe kind of confusing, but you take P to be the symmetric polynomial with the smallest maximal monomial that's not contained in the algebra generated by the elementary symmetric polynomials, and you shoot for a contradiction. P prime has smaller leading monomial, so it's necessarily in the algebra of symmetric, the algebra generated by the elementary symmetric polynomials, and then adding this thing over, you'd find that P is also in that algebra. Okay, so there's another way to do it that maybe might make you more comfortable with this whole finite number of steps. This process is guaranteed to terminate because the leading monomial decreases every time, and there are only like a finite number of monomials of like bounded total degree, for example. Okay, so now there are several important corollaries that will eventually give us the theorem that we want. So the first corollary, so this finishes this proof. The first corollary, let's say, let A be a ring f a monoponomial with roots in, let's say, an A algebra B, I'll say this a different way. Instead of calling B an A algebra, these two things are really the same. With roots in a ring B, with A as a subring, then every symmetric polynomial symmetric polynomial and the roots of f lie in A. Okay, so the proof is essentially the elementary symmetric polynomials are the coefficients of f. So they all have to lie in A. And then every symmetric polynomial is in the algebra generated by these things, which also has to be contained in A. So by the symmetric function theorem, it suffices to check that the elementary symmetric functions in the roots of f lie in A. However, okay, let's say f factors like this over b. Let's say if f of x equals this guy, x minus alpha I. So I can write as a product over its linear factors, or as a sum of monomials. I should tell you this is a polynomial in one variable. F is a sum of monomials power of x. Then each coefficient is actually just either the positive or the negative version of the ith symmetric polynomial in the roots, which is necessarily an A because A is a monic polynomial with coefficients. Yeah, I should have started with this, sorry. F necessarily has to be a polynomial in A join X. Okay. Okay. So the next corollary, which is also important, so this finishes this proof. If I have a monopolynomial with coefficients in A, whose roots all live in some big ring B, then every symmetric polynomial in the roots of f lie in A. So I'm going to let A be an integral domain. And I'm going to let, let's say, omega be an algebraically closed field. Containing A. Okay. So if alpha 1 through alpha n are the roots of some monopolynomial in A join X, then every polynomial G join alpha 1 through alpha n is integral over A. Okay, so you can see why this might become in handy. If I have like a big, so you can see how this is going to imply the result, right? If I take alpha 1 and alpha 2 and I want to show that alpha 1 plus alpha 2 is integral over A, well, I find some monic polynomial that has both alpha 1 and alpha 2 as a root, and I just check G to be the polynomial x1 plus x2. Okay. So the way we're going to do this is we're going to realize we're going to write down a polynomial which has G as a root and ends up that the coefficients are symmetric in the roots so that the coefficients have to necessarily lie in A. So I'm going to define, so proof, I'm going to define a polynomial h of x. It's going to be a product over the elements of the symmetric group on n letters, x minus g of alpha sigma 1, alpha sigma n. Okay, and this is going to have, this is going to live in omega join x. Okay, so I claim the coefficients of H lie in A. Actually, H is in A join X. So to check this, what do I have to do? By the above corollary, we need that every coefficient I guess maybe it's not so much that we need, it suffices to show. Every coefficient is a symmetric polynomial in the roots. Okay, so remember that symmetric polynomials in the roots live in A because each alpha I is the root of some monic polynomial. Okay. With coefficients in A. Note that for any, so to check this, we're essentially going to check that H remains unfixed by, or H remains fixed by the action of the symmetric group on the coefficients. For any tau in the symmetric group, H, I guess maybe this product. So if I let the symmetric group act on the roots alpha 1 through alpha n, this is going to give me something like this, T sigma 1 alpha tau sigma 2. However, it should really be sigma n. This is like a standard thing, maybe in like, you might see in like a representation theory class, or really in any kind of group theory class, where if I'm somehow averaging over elements of the group and I left multiply by a single element of the group, the whole product or sum or whatever I'm averaging remains unchanged. So that this is really can be written as a product over sigma prime now. G of alpha sigma prime alpha sigma prime of n. Okay. Which is just h of x, where, you know, sigma prime equals tau sigma. And essentially lurking in the background is that here we use that left multiplication by tau on this symmetric group actually just gives me the whole symmetric group back. Okay, left multiplication by tau actually defines a bijection on the symmetric group. Okay. So if the symmetric group acts in this way, what ends up having to happen is has to fix every coefficient of the polynomial h. So it leaves h unchanged, so it has to leave every coefficient unchanged. In particular, the coefficients of h must be symmetric polynomials in the roots alpha 1 through alpha n. Okay. Thus, h is in join x by the above corollary. And what's more, you can see just from the definition that h is monic. H is monic, and it has g x1 through xn as a root. Sorry, this should be alpha 1 through alpha n. Thus, this guy, alpha 1 through alpha n, is integral over a. Okay, so this is kind of like the main corollary that we needed. What do I want to say here? Just to kind of recap the proof idea, essentially you want to, I guess the main difficulty is cooking up this polynomial that has g as a root and coefficients in a. And the way you do this is you kind of average over the symmetric group, which forces the coefficients to be symmetric in the roots. So it's kind of this clever idea, but it's not the first time I've ever ran into this idea, and it kind of crops up in a couple different places in algebra and algebraic geometry. So it's more useful than just a one-off trick, I guess is what I'm trying to get at. And especially like the more general idea of averaging over a group to get something that's symmetric with respect to some group action is like a very powerful and recurrent idea. Okay, so let's go ahead and finish up the proof of the theorem using this corollary. So theorem, let A be an integral domain and L a field containing A. Then the collection of elements of L integral over A form a ring. So what do we need to show here? For this to be a ring, essentially all we really need is for it to be closed under multiplication and closed under addition. So proof. We need this set. I'm going to call it O sub L. This will be like standard notation. O sub L to be closed under addition and multiplication. Okay. So I'm just going to show that it's closed under addition and the other argument is almost identical. I'm going to let alpha 1 and alpha 2 be integral over A. I'm going to say, let's say let alpha I be a root of fi. Then, okay, I guess fi, which is monic. Okay. Then their product f1 times f2 has both alpha 1 and alpha 2 as a root. And then what we do is we just take G, let's say alpha 1 through, so I guess maybe I'm going to let alpha 1 through alpha n be all the roots, be an enumeration of the roots of this guy, of f1 times f2 in, let's say, the algebraic closure L bar. Then take G to be G of alpha 1 through alpha n, just to be the sum alpha 1 plus alpha 2. Okay. And, or if you want, you could take it to be alpha 1 times alpha 2. Both work depending on whether you want to show it closed under addition or closed under multiplication. And the above corollary says that these two are both integral over A, and so they necessarily live in this ring O sub L. Okay, so that wraps up this first proof using symmetric polynomials. This argument seems to, it's like more elementary in the sense that you don't need to know a whole lot of math, but the details are slightly more confusing, at least for me. And it's also slightly less general. It's a bit more like combinatorial rather than algebraic, which will be the proof that we work through next time. Okay.